which is a mouthful. But this is just one way that we have in order to be able to compare enantiomers or stereoisomers. This does not tell you, please note, that when, for example, whenever we talk about R versus S, that you stick the R in and it's going to rotate it positive 15 degrees in the polarimeter. Right? We can't do that. That's the absolute. Remember, that's the plus or the minus, because it literally would mean rotating it positive or rotating it negative. An R does not always mean it's a plus, or an S does not always mean it's a negative. You can only get that by literally using a polarimeter. But this is a way for us to be able to differentiate one versus the other. And there are people that have experimentally figured out, okay, R2-butanol is really plus or minus. Well, I don't even have it memorized, but that can put the relative and the absolute, and they've already figured it out. Okay, so I'm going to actually, let me just double check that I don't use this. Okay. So these are the rules. We have to have rules for priority for this RS system. So first, if I get something right, you want to go, I'm going to say a little different wording than the book, because go according to atomic mass. By calling it atomic mass, they first say, go according to atomic number, but that's true. But what happens if you have a carbon-12 and a carbon-13? Those are actually different, okay? And so if you have a heavy carbon versus a light carbon, whereas if we say atomic mass, you'll know, okay, carbon-13 gets priority over carbon-12. I think that's one of the lower rules down there that they say, like rule 3 or 4, and they you look and you do atomic mass or whatever, just atomic mass. Just go with atomic mass. So the higher the atomic mass or the atomic number, the higher the priority. So that's why, for example, if we compare iodine and germanium, we don't get to talk about them very often. Well, we talk about iodine, but we don't get to talk about germanium very often in organic chemistry. Which one's going to get higher priority, iodine or germanium? What's the atomic mass or the atomic number for iodine? 53 is the atomic number, and germanium is 32. So which one's going to get top priority? Iodine. Okay, or like I've already used this one. Oh, here, I can use a different one. O18 and O16. O16 is the main isotope. Which unfortunately, in organic chemistry 2, I don't think they've been able to do nuclear chemistry and organic chemistry 2 for like the last 8 years. But you guys didn't get to cover too much with isotopes. But the main isotope for oxygen is 16. But 18 it's called the heavy isotope of oxygen. So which one of these is going to get top priority, O18 or O16? O18, because that's its atomic mass. Mm-hmm. So that's rule number 1. Okay, so then, I really like the way they do that. It's the number of bonds. Okay, so what I mean by the number of bonds, let's say, for example, that we're going to be comparing a carboxylic acid versus an aldehyde, which please start looking up your functional groups and memorizing them so it doesn't make it so difficult later on for not this exam, but next exam and quiz. Because once we cover those in class, every single quiz or exam will probably have things about them on, especially at least the ones in class will definitely have things about it on there. Because that's sort of like memorizing the alphabet for organic chemistry, functional groups. See, now if we were comparing, and let's say that this was the chiral carbon, and this was the chiral carbon. Here, let me just do a better job. Let me put that on the same carbon. Okay. I'm just going to erase all this one. I mean, it's the same thing. But see, we have a chiral carbon here because we've got... Oh, whoops. Undo that. We have a hydrogen, and we've got, I don't know... Here. This. Which, let me just tell you this... Well, I won't tell you. I don't want to overwhelm your system right now about biochemistry. So this is a chiral carbon, and we know it's chiral because 4 different things. So just based off of looking at rule number 1 first, which of the 4 things is going to get top priority? We have a hydrogen, a carbon, and an oxygen. What's going to get top priority? So it's the oxygen. Okay, that's top priority because it's got the atomic number of 8, or roughly an atomic mass of 16. But then we have to compare the next. This is where it gets a little different. We have a hydrogen, a carbon, and a carbon. If we only look at those, which one would come next? The hydrogen or the carbon or the carbon? And that's what I mean by we're going to be looking at the number of bonds. Which one, maybe it's easier, which one's last in priority? The hydrogen. We know that one's absolute last. So just because, maybe I'm thinking about clothes or something, but I'm going to call this the large group, and this one's going to be extra small. Okay. Your book does not call them those, I don't believe. At least they used to not. But usually if we say top priority, second, third, fourth, whatever priority, it gets confusing. But if you think about clothing, it's a little easier. We have a large, we have an extra small. So now we have to figure out which one's the small, which one's the medium. The way to do that is now what you do is you go down the line and you look to see what the first difference is. So we see we have a carbon and a carbon, that's the same. But notice this carbon has a double bond to an oxygen and a single bond to an oxygen. This carbon's got a double bond to oxygen, but only a single bond to a hydrogen. And so when we talk about the number of bonds, this carbon right here, which I'm going to use in this color, that carbon, you treat it's got 3 bonds to oxygens. So that's what I mean, say you count the number of bonds. It doesn't look like that. I mean, it's a carboxylic acid. Whereas this one right here, it only has 2 bonds. Whoops, I told you I wasn't going to do it that way. It only has 2 bonds to oxygen, and that third bond is to a hydrogen. So that's the first difference. This right here touches oxygen 3 times. This one only touches oxygen 2 times. So the medium group then has to be this carbon. The small group is that one, because it only touches oxygen twice. And so I actually already exhibited rule number 3, and that's whenever you're talking about the same elements, you just go down the line to look at the first difference. Ooh, you really can't. First difference. So let's do some more examples, and then I'll talk about what it means with the priority. I mean, how to put these into practice, like what that means. Obviously, this is a 2-dimensional representation of something that's 3-dimensionally in space. Okay, give everybody a moment to get cut up. Normally, I don't like to draw them out this way because it takes longer, and we'll use the little stick method, but I just want to do that so it makes it easier to count bonds and things. First off, in this example, how many chiral carbons do we have? Zero, 1, 2, 3, 4. 1, 2, 3, 4, 5. All the way up to 7. So, how many chiral carbons do we have? Here's 0. Nope, we have at least 1. What does it take in order for it to be chiral? 4 different things. And so do we have any carbons there that have 4 different things hanging off of it? Yes. Okay, we only have 1 chiral carbon. It's this one right here. Because this one's got 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens. This one's only bonding to 3 things. That one's only bonding to 3 things. So that's our only chiral carbon. So now we do the rules. What's going to be our large group? Or if we want to, why don't we start with extra small? What's going to be our extra small group? Off of this carbon right here, what's the extra small group going to be? The hydrogen. And I'll tell you right now, if there's a hydrogen and it's a chiral carbon, it's going to have to be the hydrogen to be the extra small group by its very definition. So that's extra small. So then it comes up as, we have this, which you're going to find out when you memorize your functional groups. That's called a thiol. We have the thiol, we have this carbon, we have this carbon, which I call this one the black carbon and the blue carbon. Which one's going to be the large group to get the top priority? The sulfur or one of the carbons? The sulfur, because its atomic number is 16. Okay, it has a higher atomic mass, and so we know that that one's the large group. Now we just have to figure out which one is like the difference, which one's the small, which one's the medium. So we're going to find the medium because it's just better. So now the question is the medium group, or between these two, is the blue one going to get top priority, or is it going to be the black one? And so what we have to do according to the rules is you go down the different and see which one's different. What is the first order of difference? So this is ground 0. Let's see, will it let me do 2 at once? Oh, it will let me do 2 at once. That's awesome. So we're comparing these two carbons. Oh, this is kind of like fine surgery for me. So are there any difference between those 2 carbons? No. So now we go to this carbon and this carbon. Are there any differences between these 2 carbons? Yes. So the blue one touches 2 hydrogens and 1 carbon. Going forward, not going backwards. The black one touches how many hydrogens and how many bonds to carbon? 2. So which one's going to get top priority? The black one. And so I did this deliberately. This was the medium, and this one's the small group. I did that deliberately because you don't want to look too far ahead. Because yes, that alcohol, if those had been single bonds, that alcohol would eventually trump everything else. The alcohol is an OH group. The alcohol would, because an oxygen has a much higher mass than hydrogens or carbons. But because of that double bond, you always just go down the line to look at the first difference. Okay. All right. So let's say now we have the priority. How do we know, like, if that's R versus S? Okay. This is going to be the fun part. Okay, which actually I'm just going to segue directly into what's called a Fischer projection, because that's the one that's, or actually I don't have to here. What we'll do is let's draw this as a Newman projection. Let's just review what we've known so far. If we draw this as a Newman projection using that carbon, you can kind of think of it as like a half Newman or whatever. So we have the extra small group. What you do is rule 4 for doing this. Remember, what we want to try to do is try your best to put the extra small group going away from you. I can't draw. That I'm writing with my right hand, so sorry. Away from you. From. Okay, that's the word from you. So we have, this is the carbon. We're saying, okay, that hydrogen's going away. So now let's just see what's coming out. We're going to have what I'm going to call the blue carbon. I don't want to have to redraw all of that, okay? So we have the blue carbon, we have the black carbon, and we have the thiol, the sulfur. We've already assigned these. The H was the extra small group and it's going away from us. The blue was the small, this one was the medium, and this one is the large. So the way to do this, using the Kohn-Ingold pre-log method, which also works with the Fischer projections, which is coming up, is we always, we want to draw, now you ignore the extra small group. We want to draw a line that goes large, medium to small. Top priority to low priority. So if we do that here, let me change the color. Or actually what I'll do is, let's do a highlight. Oh, that's a really big highlight. I don't like that. Okay, so if we go to large, medium to small, we now have to ask, is it going clockwise or counterclockwise? Counterclockwise. And so what they do is, if it's counterclockwise, which I'm just going to call it C-clock, that equals S. If it's clockwise, it's R. It's supposed to be an R. I really can't write today. So this one is S, as long as the extra small group is going away from us. If you do the opposite, it's the opposite of what you think. Now, some people think about clockwise and counterclockwise. Some people have problems and they need to think about it this way. You can also think of it this way. Clockwise is the same thing as if it's going towards the right. But remember, this is like a dial, okay? Because then some people overthink it. You're turning something to the right, then on the bottom side, you're turning it towards the left. You know what I'm saying? So the initial turn is to the right. That's why you say clockwise. So once again, right, R, clockwise, S, left, counterclockwise. The S comes from sinister, which I think is just because that they were, I don't know, it's not racist or ethnocentrist or whatever, xenophobe or whatever. It's because back traditionally they thought left was evil. So sinister, evil, left, sin, all that kind of stuff. Which is just against left-handed people. Sorry. But yes, whereas R is the right. But that's why it's S. So let's just do do more examples. Let me get rid of all this. And give you guys a chance to get caught up. And I'm doing, it's not, my method takes a little bit longer time than what some people do, but if you do my method, especially when you do what's called Fischer projections, if you work it out and you understand the logic, I mean, I see people do really, really, really well, okay? And so this may get to be where it looks redundant, but just trust me, if you do my method, usually, as long as you understand the method and you understand those basic rules, then you'll do well in those quizzes and exams. Okay. So if we look up here, and these, one question we have is, are these two compounds, are they identical or are they enantiomers of each other? Because that's a chiral carbon. Those are your two options. Sometimes, and some people can just look at that and say, oh, those are identical, or oh, those are enantiomers. I am not one of those people, okay? So that's why sometimes you just have to compare, like, are these two things really identical in three-dimensional space, or are they really enantiomers of each other? So, okay. So what I do is I call the looks and is. That's my, and it'll make sense once we do some examples, I hope. If we look at the one on the left, so we have here, these are the same, first of all, just check to see if they're the same four functional groups. If they're not the same four functional groups, then the answer is neither, because they're two completely different compounds. But we have a hydrogen, an alcohol, a fluorine, and a methyl group. It doesn't matter with me if you want to start with extra small or if you want to start with large, but you just decide. Who wants to go first? You want to start with extra small or large? Extra small? Okay, what one's the extra small group? Hydrogen. And that's true for both of these. So that's why I'm going to go ahead and put it on both. Now let's go to the other extreme. What gets top priority? What's the large group? Fluorine, methyl, or the alcohol? Fluorine, so that's large. What will be medium? Alcohol is medium. And so by process of elimination, the methyl group is small. So now what we need to do is you always connect large, medium to small. Large, medium to small. And I draw my little arrow in. Okay. Oh, I forgot to put it. I usually put a little asterisk to show, like, because we're going to see like what happens when you have more than one chiral carbon in a moment. So we only have one chiral carbon to work with. So this is why I do my looks. Since when we connect large, medium, and small, is that going clockwise or counterclockwise? Counterclockwise, or you can think of it to the left, so that it would look like it is R or S. S. So it looks like it is S, I'm sorry. The is when now we just have to think, is the extra small group going away from us or not? It's easy when you only have four things and you can imagine twirling it, but what's going to happen is, what if it's cyclical, or what if we have lots of things hanging off, and not lots of things, but lots of chiral carbons, and we can't really just pick it up in our mind and move it around. So just look, is the extra small group going away from us? Yes, it's hashed. So that means the is the same thing as it looks, and so, you know, yep, it really is the S enantiomer of that. Now we go to the other side. We connected our large, medium, small. So is it going clockwise or counterclockwise? It's clockwise, so it looks like it is. It looks like it's R. Now we have to ask ourselves, is it really R? Is the extra small group coming towards us or away from us? It's coming towards us, and so it's the exact opposite of what it looks like. So these two compounds really are the same thing. Because once we get to really big things, especially sugars that are biologically relevant molecules, most of the molecules in our body are not really tiny like that. We're talking about things that are really huge. We can't just put it's not just a simple tetrahedral that you can imagine twirling like a camera on a tripod. Please don't twirl your cameras on a tripod, so. Yeah.
So if it looks like one thing and the extra small is towards you, it's opposite.
It's the exact opposite. Because this one we can imagine, okay, let's hold the methyl group as the top of the camera part, and we just rotate it to where the hydrogen's not going behind us, it actually inverts the sign. Okay, but like I said, some people can just look at things on 2 dimensions and just see 3. I was not one of those blessed with that gift, and so I have to actually set and do all the rules. All right, so that brings us up to what's called a Fischer projection. Okay, and let me make sure I spell Fischer correctly. Yeah, that's what I thought. Fischer projections. I don't like this color. All right, it's spelled with a C. Fischer projections are quite useful, especially when we talk about biomolecules, because now we're talking about things that get really large. They may have multiple stereocenters. Right? So the problem is, like, sugars are notorious biochemical or biological molecules. They have lots of chiral carbons. That's why, your body utilizes one specific, I want to say it's D, that may be wrong, D glucose versus L glucose. That's what I should know off the top of my head, but I forget. I'm pretty sure it's D. And so that's the one that your body has to utilize. And so we do have enzymes and things that can break it apart and to change it around. But we have to be able to tell, there are 6 different carbons, and what is it, 3 or 4 of them are chiral carbons, and so that's why it gets really, really complicated. So let's just start with a simple Fischer projection. Right? So let's say that this is the compound. That's supposed to be a wedge. Oh, that came out wedgy. Okay. This one's relatively simple. We could actually sit there and do just like what we've been doing, because we've got the extra small group going away. First of all, kind of give it away. Are any of the carbons chiral? Yes, that middle one right there. It's got 4 different things hanging off of it. It's the only one that's chiral, by the way. So that one's relatively simple. However, we can imagine that what if, the way it's drawn like that, but what if it was drawn to where it looks something more like this? I mean, you can imagine it being drawn the same way, or what if it's given to you like this? And let me see if I can draw it. I'm going to have to write it out. I can't do it the way that your book. Okay. So now you can, but it becomes really cumbersome. You have to draw in the wedges and then draw in the hashes and stuff. And so what you can do is what's called the Fischer projection. And what they do, it's actually really nice, is you draw everything like this. For every chiral carbon will be an intersection. Like this is the chiral carbon. But, this is what that will translate to. That's supposed to be C. That's a Fischer projection. These 2 things are the same thing. So this equals that. So in a Fischer projection, I'm going to draw it this way now. And just say A, B, C, and D. That C is not a carbon, but what it means is that, what is that? The line A and B is coming towards you. So the vertical line is coming toward you. I'm sorry, that's a horizontal line. I said wrong. The vertical line is going away from you. A and B is horizontal. So the vertical line is going away from you. Geometry was one of my hardest subjects. And I really struggled in geometry in the beginning, like the first few weeks when I was in high school, because I was too embarrassed to have to tell the teacher I couldn't tell the difference in the colors. Did you see everything in colored chalk? Yeah, it was lost on me. So then finally I got over my pride and told her, and so then we found different ways. I ended up getting an A in the class in that semester, but it was one that I really struggled with. Okay. So what I'm saying is anything when we do Fischer projections, and that's probably the way you've seen in sometimes you'll see this in biology books. For example, they'll show a sugar that looks like this. Biochemistry does this all the time too. Like that's a sugar. And that's just a Fischer projection because it's easier to show that. And that way you can sit there and figure out, and we'll do examples of that in just a moment. So you don't have to write that last one down. I just wanted to show you what a Fischer projection looks like. But in that example, anything that's on the horizontal line means it's coming towards you. Anything that is on the vertical line means it's going away. So that's why let's go back to this example, which you should draw, because now we can figure out the R and the S. Okay, so once again, I'm just going to move this on up. If you go back to this example right here, oops, sorry, wrong one. Right here, this carbon, what's going to get the top priority? What will be our large group? The alcohol. Okay, so that's large. What will be the medium group? What's going to be the medium group here? The one at the top or the one at the bottom? The top. By the way, that's called an aldehyde. So it's an aldehyde. But yes, that one's going to be medium. This one's the small because it's got just an alcohol that it touches. Whereas that one makes 2 bonds with oxygen. And then this is extra small. Once again, the quick method is as long as it's chiral and it's got a hydrogen, that hydrogen has to be the extra small group. So now what we're going to do is we're going to do our looks is. That's supposed to be looks. Looks and is. We always go large, medium. You just ignore the extra small. Large, medium, small group. So, when I draw it, is it looking like it's an R or looking like it's an S? Just looking like. Let's just not skip any step. It looks like it's S, and it does that because it's going counterclockwise, or it's going towards the left from the large group, right? Now we have to ask ourselves, is it really R or is it really S? This is our extra small group, and in the Fischer projection, is it coming towards us or going away from us? Coming towards, so therefore, is this really S or is it really R? This is R. Wow, you guys already sound like a cult. So I've been successful. So, okay. All right, so let's go and we'll do another example here. We're going to do, it's called 2,3-butane-diol, which I think I may have even written down towards the end of the last class. It's one that's oftentimes given in books. So I'm just going to scroll this on up. So we want to look at 2,3-butane-diol. Which this is the way it is drawn out. Oh, that is not good. This is the way it is drawn out. Butane means it's got 4 carbons. The OL ending means it's an alcohol. Okay. And since there's 2, it's di 2,3-butane-diol. First of all, are any of the carbons chiral on 2,3-butane-diol? So we just go through, and what we look at is we start here. Does this one have 4 different things hanging off of it? No. Does this one have 4 different things hanging off of it? Yes. It has an alcohol, a methyl group, all of that, and a hydrogen. Okay, and this one also does, and this one does not. Okay? And so there are 2 chiral carbons on this one. So what we're going to do is we're going to draw all of the possibilities. Which sounds, we're going to draw them as Fischer projections. So that top carbon was a methyl. We have one that's an alcohol, hydrogen, and hydrogen. And the way to do this, if you remember, just imagine a mirror, and I usually have to draw it this way because I'm a little slow when it comes to imagining things in three-dimensional space. And the easy way to do that is we want to draw, whoa, that's really crooked. But on the top, well, the top is still a methyl and the bottom is still a methyl. But if this was a mirror, this alcohol that here is the closest to the mirror, so its enantiomer would also have the alcohol closest to the mirror. Right, because you're looking at the mirror image. Kind of very Alice in Wonderlandian, like you enter that mirror. Actually, I don't know that that's actually a part of Alice in Wonderland, but it kind of sounds like something that would be Alice in Wonderland. Then we have two more. I'm just going to, oh, of course that doesn't. Well, hopefully you don't mind that I wrote that the name is over the R and the S now. We have two more possible. The methyl, my dystonia is starting to act up, so I apologize that everything's starting to look shaky. Now the way to do this is let's keep the top carbon the same. So we still have the alcohol closest to the mirror, but all we need to do is switch the bottom one. So it now also has the alcohol closest to the mirror. And once again, just imagine the mirror. You draw it. So these are the four possible. And you know what? There's an actual mathematical formula. And this is one that I do want you to know. It's one that you just have to memorize, but it's really easy. I mean, if you've been in, I don't know if it's calculus or what math class it falls under, but you probably have to do like series, like Taylor expansion series and things like that. Which I don't remember any of their names, but this one actually is practical. So I want you to know this one. This was easy enough to do with 2,3-butanediol, that there's only four possibilities. But the mathematical formula for the possible number of stereoisomers, it's really simple. I say possible because remember there's something called a mesostructure, but the number of theoretical is equal to 2 to the power n. And n is the number of chiral carbons. That's why I told you it's a really easy one. So in butanediol, since over here we had 1 chiral carbon, 2 chiral carbons, 2 to the 2 is 4. Okay? But that's the number of theoretical ones. So let's start here. Oh, whoops, I did not mean to do that. Let's start the top left one. If we look at that top left structure, this one and this carbon right here, what's going to get top priority? We have a methyl, we have an alcohol, a hydrogen, but I call everything else. Okay, which one's going to get top priority and will be the large group? The alcohol. So that's large. Which one's going to be the medium? This is where sometimes people struggle. Is it going to be, we know it's not going to be the hydrogen. Is the medium going to be methyl, or is it going to be this carbon down here, the everything else carbon? It's the everything else carbon. So I'm going to put the medium here. That's small, and like I said, extra small. Now if we look at the second carbon, which I'm going to put in, what is this color down here, blue? Whatever this color is. Okay, so the second carbon down there, we already know, they're the same things hanging off. We know that that's the large group. That's going to be extra small. This is the medium. And that one's a small group. It's not always going to be true. Like sometimes they won't be the same. So don't just assume that, you know, we'll do examples. You'll have lots of examples, I'm sure, between the quizzes and in class and everything. So I'm now going to have, let me see if it'll let me do erasing. No. I really wish it would let me move some of the stuff over. Oh, good. Hallelujah. So we got to do our looks is, And we have a looks is. So carbon number 1, this one up here, we have large, medium, and small. Remember, just ignore the extra small group. So we go large, medium, and small. What does it look like? Does it look like it's R or does it look like it's S? It looks like it's R because it looks like it's going clockwise. Now we have to ask ourselves, is it really R or is it really S? Is the extra small group coming towards us or away from us? Towards. So it really is S. Okay? Now we want to do the same thing with the bottom one. We go large, medium, small on it. Does it look like it's R or does it look like it's S? Oh, we got a debate. So, I mean, it's not, it's not quite like, Trump versus Hillary here for the debate. But who wants to take it? Is it really R or is it really S? Who wants to make their argument here? It's R. It's going clockwise. Like I told you, it's not nearly as riveting. Now the question is it really R or is it really S? It also is really S. Okay? And once again, it's because this extra small group, I know that, thank you, is coming out towards us. Okay? And so what we're going to do when we pick up, so this one, actually, if we were going to name this, it would literally be named S. Sometimes they would put like 2S, 3S, butane diol, and the S is in parentheses. Okay? And so on your own, what you may want to do is go through and figure out, and what would be a big help, is figure out these other 3. Okay? And we'll pick up in the next class what that is, what that means.